massive eruption spewing scorching lava from Hawaii's second largest volcano. The glowing goo rippling across a crater at the top of Kīlauea on Hawaii's Big Island, where fountains are shooting lava over 200 feet high, according to the U.S. Geological Survey.
This is what we know right now. NASA's cutting-edge satellites have detected subtle but unmistakable ground inflation beneath one of the world's most restless volcanoes, Kīlauea, deep in the heart of Hawaii. What began as the faintest rise in the land, almost imperceptible to the eye, has now become a scientifically significant signal. It's the kind of change that volcanologists have learned to heed, a gentle swelling that can herald powerful eruptions, or quietly subside, leaving behind little but questions and confusion. The ground is not the only thing shifting. A series of linked discoveries is reshaping our understanding of the island's geology. Recent studies, made possible by the latest analytical techniques and satellite technology, have revealed the presence of gold and other precious metals within Hawaii's volcanic rocks. These findings trace the path of rare elements from deep beneath the surface, hinting at connections stretching towards the Earth's interior. Monitoring networks are alive with signals. Earthquakes tremble in patterns that modern sensors can now capture and interpret, each telling its own story about the magma chambers below. In this broadcast, we break down the sequence of discoveries shaking up the scientific world right now. We trace how NASA's breakthrough observations connect with revelations from the rocks, the shifting seismicity, and the dynamic interplay of Hawaii's geology. Are these changes building to something monumental, or is this just another chapter in a land famous for the unexpected? Stay with us as we dig beneath the surface. Chapter 1. Ground inflation detected by NASA. Imagine the ground beneath your feet rising, slowly but surely, as if some invisible force is breathing into the island itself. That's exactly what NASA's Earth observation satellites have captured on Hawaii's Big Island. But what is ground inflation, and why does it spark urgency among volcanic scientists? Ground inflation is a swelling of the Earth's surface, a direct sign that magma is accumulating beneath a volcano. Using advanced interferometric synthetic aperture radar, NASA's instruments can detect changes in land elevation as subtle as a few millimeters. On Kīlauea, these minute uplifts have triggered a flurry of activity among local and global geologists. Scientists monitor these changes closely, understanding that even small uplifts can precede significant volcanic events. So why do these gentle bulges matter so much? When magma enters underground chambers, it presses against the overlying rock, lifting the ground piece by piece. Sometimes, inflation recedes without fanfare, the magma dissipating harmlessly, but other times, such changes can precede eruptions, as decades of observation have shown. Could current inflation be the harbinger of a new eruptive phase, or merely a part of Kilauea's ongoing cycle? Only time and vigilant measurement will tell. The lesson is clear. Hawaiian volcanoes do not swell without consequence, reminding us that even the subtlest rise can be prelude to dramatic surface changes. Chapter 2. Earthquake swarms, signal or warning. Sudden clusters of earthquakes are again rattling the Big Island, echoing through the network of seismic sensors dotted across Hawaii. Is this just background noise from a restless Earth, or an urgent alert from the planet itself? Earthquake swarms, brief, intense bursts of seismic activity, often act as the heralds of volcanic changes. Scientists scrutinize their character. Are the quakes shallow or deep, clustered or dispersed? When swarms erupt near Kīlauea, they're frequently associated with the movement of magma, which cracks open new pathways in the crust. The location and frequency of quakes provide vital clues to what is brewing beneath the surface. Yet, not every swarm signals imminent eruption. Sometimes magma movement stalls, pressure is relieved, and seismicity quiets without surface consequence. The important distinction lies in the patterns. An uptick in quake frequency or intensity, particularly during ongoing ground inflation, heightens concern. Is the Earth shaking out of habit or in anticipation? Scientific models and decades of monitoring suggest that only when seismic swarms coincide with other indicators, such as gas emissions or increased ground uplift, do alarms escalate. For now, the tremors keep researchers vigilant and residents alert, waiting for further developments from below. Chapter 3. Shawn Willsey, Decoding Magma Movements. The volcanological world listens closely when Professor Shawn Willsey shares his insights. What has his research revealed about Kīlauea's subsurface activity, and how should we interpret his findings? Shawn Willsey, a prominent geology professor, has provided recent updates on the geologic pulse beneath Hawaii's most active volcano. By examining patterns in ground inflation and seismic activity, Willsey and his colleagues are piecing together a dynamic picture of magma movements within Kīlauea's subterranean plumbing. Their analysis points to a complex, evolving system, magma rising, at times pooling, occasionally shifting laterally as it searches for weaknesses. For those living nearby, Willsey emphasizes caution and patience. Rushing to conclusions without comprehensive evidence can cause needless panic or, worse, complacency. By carefully reading the signals, seismic events, ground deformation, gas emissions, scientists work to narrow the window of uncertainty, aiming to identify unrest before it escalates into eruption. Is forecasting Hawaii's next eruption a matter of reading crystal balls or cold, hard data? According to Willsey, every dataset is a clue. Only when multiple signs confirm each other do experts feel confident enough to issue warnings. Chapter 4. Gold in Hawaii's volcanic rocks. Imagine finding that the land beneath you contains precious metals, elements carried up from vast depths by ancient earth processes. Does this new finding change Hawaii's story as more than just a volcanic archipelago? Recent scientific studies have confirmed the presence of trace gold and other precious metals in Kīlauea's volcanic rocks. These elements were not deposited by surface events. Analysis shows they have a deep origin, surfacing as magma rises and erupts. The detected metals, including gold, palladium, and other rare elements, offer scientific intrigue rather than economic promise. But how does such gold make its way to the distant islands of Hawaii? The answer lies in the ascent of mantle plumes, hot, buoyant columns of material rising from deep within the Earth's mantle. As magma rises, it carries with it metals and volatile compounds, eventually releasing them during eruptions. Over thousands of years, each outflow leaves a chemical imprint on the island's geology. Does this make Hawaii an untapped gold mine? Geologists say not. Concentrations are far below what would interest miners. The real treasure is the window it provides into Earth's interior and the processes that move metals from depths to the surface. A rare look at the ongoing geological alchemy beneath our feet. Chapter 5. Earth's core, leaking treasures? The Earth's core, a searing, hidden realm, has long inspired both geological inquiry and scientific mystery. If Hawaiian volcanic rocks harbour elements from this deep, what does it imply about Earth's inner workings? Recent studies suggest a chemical connection. Earth's core may be gradually supplying gold and other precious metals to the surface, carried upward by mantle plumes, and ultimately locked into volcanic rocks. Chemical fingerprints within Hawaiian samples align with deep Earth origins, supporting the idea of a long, slow exchange between core and crust. How are these elements transported? It is the slow but relentless convection of the mantle, a cycle of heating and rising material carrying along metals scavenged near the core mantle boundary. Hawaii's position above a particularly persistent mantle plume makes it, and its volcanoes, a natural collector of these deep Earth elements. Do eruptions significantly enrich Earth's surface with precious metals? On the scale of mining, the arrivals are minuscule, but for science, each new measurement adds evidence about how dynamic and interconnected the Earth's layers truly are, reminding us that even after billions of years, our planet continues to trade materials between its innermost depths and its outer crust. Chapter 6. John Dvorak and the Eruption Timeline. When it comes to the timing of volcanic eruptions, veteran volcano specialist Dr. John Dvorak is an authority. But just how far can monitoring Kīlauea's inflation take us toward predicting the next eruption? Dr. John Dvorak has decades of experience observing volcanic behavior, from seismicity to ground deformation. His research indicates that ground inflation is never a simple countdown. Rather, it's a complex signal that must be considered alongside others. Sometimes, long periods of inflation are punctuated by sudden deflations, a slow release of pressure as magma migrates laterally or escapes through unseen cracks. How reliable is Dvorak's timeline for eruption forecasting? The reality is fraught with uncertainty. Eruptions may follow inflation within days, or only after months, or not at all. Occasionally, Kīlauea springs into action unexpectedly. Other times, tension is eased by minor eruptions or the release of vapor and gas. Is it possible to pinpoint the next big event? Dvorak's answer is caution. We can read the signals, but the volcano writes its own timeline. Prediction depends on converging evidence across many channels, not on any one sign alone. Chapter 7. Plate Tectonics beneath Hawaii. Hawaii's volcanoes rise not from tectonic plate boundaries, but from the middle of the Pacific plate itself. What makes the Hawaiian setting so geologically unique? While most volcanic activity around the world is fueled by tectonic collisions and subductions, the grinding and diving of plates, Hawaii sits thousands of miles from such boundaries. Instead, it is set atop a powerful mantle plume, a localized, persistent upwelling that forces magma through the fixed oceanic crust. This hotspot geodynamics powers the regular cycles of inflation and eruption seen at Kīlauea and its neighbors. Why does this matter for ground inflation? Unlike volcanoes at plate boundaries, Hawaiian eruptions are strongly influenced by the surge of deep-sourced magma beneath a stationary plate. Each upward pulse reshapes the surface, causing measurable uplift and sometimes leading to spectacular lava flows. Are such processes found elsewhere on Earth? Yes, but rarely so clearly expressed. Hotspots like Hawaii and Iceland give scientists rare opportunities to study how deep mantle activity influences surface volcanism, expanding our understanding of the forces that build continents and islands. Chapter 8. Earthquake patterns, geography and depth. Not all earthquakes carry equal meaning. Some flicker near the surface, others are rooted deep within the earth. Is there a deeper logic to their patterns beneath Hawaii? Researchers mapping recent earthquake swarms have found that both the location and depth of tremors often reveal the path of migrating magma. Shallow quakes, within 5 kilometers of the surface, tend to indicate reconfiguration or movement within the volcano's shallow plumbing. Deeper events, extending 15 kilometers or more below ground, are associated with movement along major structural features, such as the inflow of magma from the mantle. Can these patterns help predict future activity? While no single set of tremors spells certain eruption, mapping depth, frequency, and localization helps volcanologists build a 3D picture of stress and movement below. Over time, and with enough data, these patterns become critical tools for risk assessment and event forecasting. Do deep quakes guarantee a major event? Not necessarily. Each sequence must be interpreted within its context. Meticulous tracking across years and cycles is necessary before scientists can reliably interpret what the planet is signaling. Chapter 9. Caplan-Auerbach, Seismic Sleuthing. Cracking the code of volcanic tremors takes more than sensitive instruments. It requires intuition shaped by experience. Enter Dr. Caplan-Auerbach, a seismologist renowned for her work deciphering seismic signals at active volcanoes. Caplan-Auerbach's expertise lies in distinguishing different tremor signatures: the sustained vibrations suggesting steady magma movement, sharp cracks that signal brittle rock fracture, and subtle baseline hums marking quiet interludes. By cross-referencing seismic changes with gas releases and ground inflation, her research reveals connections otherwise invisible. Can these techniques predict exactly when Kīlauea will erupt? Not with certainty, but they greatly enhance the ability to detect worrisome trends, such as escalating unrest. Caplan-Auerbach's insights illustrate how blending seismic data with geological and chemical measurements offers the best chance to catch early warnings. Is there such a thing as a perfect seismic fingerprint? Caplan-Auerbach notes that every eruption rewrites the pattern book. Kīlauea rarely repeats itself precisely. Success lies in never underestimating the volcano's power to surprise, and in uniting data with seasoned judgment. Chapter 10. NASA Technology, a new volcanic lens. What happens when the world's most sophisticated space agency turns its gaze toward terrestrial volcanoes? The result is a leap forward in monitoring, forecasting, and preparedness. NASA's observation technologies, from radar interferometry to thermal imaging, provide a near real-time window into Kīlauea's inflation and movements. Instruments initially designed for lunar or Martian landscapes now capture the shifting topography of Hawaii in unprecedented detail, including millimeter-scale ground changes and thermal anomalies invisible to ground observers. How does this data change risk management? Traditional field observations have delays and gaps. NASA's satellites generate broad, frequent, high-resolution coverage. This continuous flow of images and measurements helps scientists detect inflation trends early, monitor change between eruptions, and forecast when patterns might become dangerous. Could this technology tip the odds in favor of early warnings? The answer may lie in the combination of satellite data, ground sensors, and human expertise. Together, they create a global, dynamic model of volcanic risk, an evolutionary step in how we watch over hazardous landscapes. Chapter 11. Gas emissions, chemistry of unrest. A whiff in the air can spell warning long before lava erupts. But do volcanic gases always tell the truth? As Kīlauea's inflation continues, gas monitoring systems, both on the ground and now with satellite support, track rising emissions of sulfur dioxide and other volcanic gases. These releases, which occur as magma nears the surface and decompresses, are vital clues about unrest. Spikes in sulfur dioxide often correspond with increasing volcanic activity, serving as an early warning. However, not every gas flare signifies eruption. Background levels fluctuate with wind, weather, and the volcano's mood. Only when sustained increases in gas emissions align with ground inflation and other signs do experts consider raising alerts or restricting access. So, does a sudden sulfurous breeze forecast immediate danger? Usually, it means magma is rising and degassing, signaling elevated unrest. The true risk is found in patterns. When gas, seismic, and geodetic signals synchronize, authorities and communities brace for change. Chapter 12. Comparing Kīlauea to global volcanoes. Hawaii's volcanoes are famously active, but how do their rhythms compare to the world's other great erectors? Is Kīlauea uniquely reliable in its volatility? Around the globe, volcanoes from Iceland's icy peaks to Indonesia's lush slopes exhibit cycles of inflation and outburst. Yet Hawaii's Kīlauea is distinct for its persistent, frequent activity. Unlike stratovolcanoes, whose outbursts may be centuries apart, Kilauea's cycles continue year after year, driven by a steady mantle hotspot rather than the unpredictable friction of colliding plates. What does this difference mean? It positions Kīlauea as an invaluable laboratory for volcanologists, a site where the underlying processes driving volcanic change can be observed in near real time. Lessons from Kīlauea ripple outwards, informing risk models for more hazardous volcanoes near populated areas. So, is Hawaii's drama a global anomaly or a volcanic archetype? The scientific consensus is that it's both, a unique case study and an ongoing benchmark for studying Earth's restless geology. Chapter 13. The legacy of past eruptions. When the ground swells, it echoes with the memory of past eruptions. What guidance do these earlier disasters offer, and what warnings echo in today's unrest? Historic eruptions, like Kilauea's dramatic events, including the infamous 2018 crisis, have shaped not just landscapes, but communities. Each eruption is etched into the island's geological memory as layers of basalt, ash, and transformed topography. Researchers constantly sift through these records, matching inflation episodes, earthquake trends, and chemical signatures with past precedents. Can today's data replay yesterday's disasters? Scientists closely compare present changes, rising ground, tremors, gas releases, with the weeks and months leading up to historic eruptions. Sometimes patterns line up, similar swelling, equivalent seismic clusters. But the volcano is unpredictable. New behaviors emerge, and no two sequences are ever identical. Does history repeat itself, or does it simply provide context? For those who live and work near Kīlauea, every new sign is viewed through the lens of past events, an ever-present lesson that no signal should go ignored. Chapter 14. Future monitoring, from surface to space. Will science ever forecast every eruption with unwavering accuracy? How are the strategies for tracking Hawaii's unrest evolving? Volcano monitoring is changing fast, from hazardous fieldwork to edge-of-space observations. New tools now track ground deformation, seismic unrest, gas emissions, and thermal shifts with remarkable precision. Drones survey craters, satellites scan broad landscapes, and continuous sensor arrays deliver streams of data to scientists in real time. But is more data the only answer? The challenge is distilling meaningful signals from the flood of readings, turning raw numbers into insight and warning. Artificial intelligence and machine learning are increasingly deployed to sift through terabytes of information, flagging unusual changes for expert review. What comes next for Hawaii's volcano monitoring? A fusion of space-based views, ground science, and automated analysis promises earlier, more accurate warnings, so long as we remember the volcano itself holds the final word. The restless planet beneath Hawaii demands humility, patience, and relentless curiosity from all who seek to understand it. Chapter 15. Forces at work. The interplay continues. As the ground under Kīlauea quietly rises and sensors continue their endless vigil, the story of Hawaii's volcanoes remains unfinished. Each day brings new data and new questions. A gentle ground uplift, a spasm of seismicity, a measurement that hints at metallic origins buried far below. Certainty is rare, change is constant. The interplay of deep earth forces, magma surges, escaping gases, rare metals marking ancient journeys, unfolds like a living legend. Technology, from NASA's satellites to the geoscientists' console, has given us new insights and warnings, but the art of prediction remains an imperfect pursuit. The world beneath Hawaii is as enigmatic as ever. For those living at Kilauea's foot, vigilance is woven into daily life. Swelling ground and clustered earthquakes recall an island born of fire and sustained by change. For researchers, each anomaly is both a challenge and a chance to explain, to anticipate, and above all, to respect the scale of what remains mysterious. The next chapter, already taking shape far below, will rise into view in time, signaled by magma, rumbling faults, or a change in the winds of volcanic gas. The eyes of the world and the satellites above are fixed on Kīlauea, waiting for what comes next. On this restless planet, even solid ground is but a passing phase, a reminder of Earth's ongoing transformation and our enduring quest to understand it.